Okay, so once again for this one, we are going to start out with, I'll do this kind of like intro and the theory behind diffraction, and then we'll do some math examples in the next one. So I'll split this topic kind of into two, okay? So today is all about diffraction and interference, okay? So diffraction and interference. So before we really jump in, let's just kind of go back a bit and think about waves again so that we can kind of see where we're going with this. Review where we've been so we can see where we're going. Okay, so I'm going to kind of start with a side view here. Okay, we're going to start with, I can put a disturbance in and then a wave, which remember is the motion from a mechanical wave, which is the motion of energy through a medium, right, will propagate outward. I can also kind of get just a continuous wave here by just continuous drip. So we have a crest, trough, crest, trough, crest, trough. Okay, remember the water is staying here. It is vibrating up and down. The wave is propagating this way, and the medium is moving perpendicular to it. Okay, let's go ahead and look at this from above just so we can visualize what's going on here. So I'm going to switch to the top view just because these diagrams I do, now that you're okay with it, okay, what do these diagrams actually represent? So we have a crest traveling out and a trough, crest, trough, crest, trough. Okay, I could increase the frequency, right? Make more drops happen. What will that do to wavelength? Since they're still traveling through water, right? They're still traveling through water, so they still travel at the same speed, but since the frequency is now faster, the waves kind of get bunched up. So if the frequency increases here, right, but they're still traveling the same, the distance from crest to crest gets smaller. They get bunched up. If I lower the frequency, now there's more time between crests and troughs, more distance between crests and troughs, I should say. Okay, again, a reminder that sound is a wave, right? I can send out sound waves. You can even see the particles, right? That's what a sound wave is. It's a longitudinal wave where the particle motion is in the same direction as wave propagation. So pick a red particle and watch it. Notice how it only ever moves in the same direction as the wave is moving, or exactly against that direction, but never perpendicular, never up or down. Okay, you can even do both, and you can kind of see now how the wave is moving. Crest, trough. Troughs where there's rarefaction, crests where there's compression. Anyway, this is not about sound, right? And we can do the same with light. So imagining light as a wave, well, not imagining light as a wave, light being a wave. Okay, so if we imagine light as a wave, we see it like this, right? If we change the frequency, purple, we know violet has a much shorter wavelength, and sure enough, when we increase the frequency, we get a much shorter wavelength. Red has a much longer wavelength. Sure enough, when we go to red, right, at a lower frequency, we get a much longer wavelength. Okay, so all of this is just to remind us of these kind of diagrams and these kind of views of waves. Let's now pause for a sec, and we're going to take a look at something that we didn't really cover in Physics 20, though it wouldn't have changed anything we did in Physics 20. It is going to have some effects now, okay? That is something called Huygens principle, and I don't think that's actually how you pronounce his name, but it's something like Huygen. It's very Dutch, okay? I'm going to go with Huygens because that's what most people say. So Huygens principle is what explains this property of diffraction. So what is diffraction? It's basically as a wave passes a barrier, its direction changes, okay? And this causes the wave to bend around the object. Why? It comes down to Huygens principle. So Huygens principle is basically that, yes, you have your wavefront. But what if we imagine each wavefront as being made of infinitely many tiny point sources called wavelets? Okay, so when we look at this diagram here, right, yes, you have your wavefront, okay, but we could just say, yeah, but that wavefront is just made up of a billion tiny little point sources, right? So the wavelets are little point sources of waves, little circular waves that are propagating outward just at the same speed of that wavefront that they're part of, right? So the wavelets propagate outward at the same speed as the wave they are part of. So the line tangent to the front of those wavelets, well, that's just your wavefront, right? So you can see here, we have a linear wavefront, but we could imagine, hey, it's just made up of tiny little wavelets. Imagine dropping a billion little pebbles and watching the wavefront all just go at the same time, right? A billion pebbles into a stream, and then following the front edge of all of those billion little pebbles, and you have Huygens principle. You have the idea of a wave is made of billions of tiny point sources of tiny little wavelets. Okay, a wavefront is. What's the big deal? Why does that matter? Well, it's going to explain some of the weird properties we see. Okay, so now we're going to revisit this, go back to the simulation. Now think of Huygens' principle as we do. Okay, so why do waves spread when they hit a barrier? Well, let's make some waves. Here we have a crest coming, but remember, now we're going to say, okay, this wave front is actually made of tons of little circular wavelets that are all propagating outward, but they just so happen when you draw a line tangent to all of these billions of little tiny little circles, they just make this line, okay? Why does that matter? Well, look, okay, think about it. All of those wavelets up here just got blocked. All of these wavelets down here got blocked. They were always going forward in a circle, okay? It's just that all of those circles add up to a line. But now there's a little wavelet there, and there's a little wavelet there, and they're going to continue like a pebble in a lake. They're going to continue like a pebble in a lake to spread out. Aha, right? Notice we've changed the shape of the wave by passing it through a little barrier, okay? We could do two slits. That's going to be important later, okay? So by using Huygens' principle and imagining, okay, this is a bunch of little circles that are all propagating out at the same speed as the wave front itself, so that when we draw a tangent to all of those little circles, it ends up looking like a straight line. That changes once they hit a barrier. That's why waves encountering a barrier can change direction, right? If you don't buy into diffraction, well, remember that sound is a wave. Can you hear someone around the corner? Yeah, because the wave can bend around the corner, right? So again, Huygens' principle right now, don't worry, we're not even applying it to light yet. Okay, we're going to. Okay, we're just saying that's what a wave is. It's made up of a bunch of little tiny wavelets. Okay, so when a wave encounters a barrier or a thin gap in a barrier, the wavelets just continue to radiate outwards in circles. But the shape of the wave changes because some wavelets get blocked, right? So this thing was going this way, and these wavelets got blocked. So this little wavelet here is going to go, okay, I'm just going to keep radiating outward. And there you go. You have the changed shape of your wave, right? Now it's bent around this. If these were particles, that wouldn't happen. They would just get blocked and that would be it, right? They've bent around it. Okay, same thing here. If you were sending a stream of particles through, they would just go through like that, right? Instead, a wave is made of wavelets. A wavelet, a point source here now that gets through. Yes, all these ones get blocked, but this little point source here is going to now radiate outward circularly, right? Same thing here. These all get blocked, but a little point source here goes like circular outwards, right? So these ones are still part of this wavefront. These ones are still part of this wavefront. However, here they propagate that way now. Okay, so this bending of a wave around or through a barrier is known as diffraction. And it is obviously purely a property of waves, right? Imagine a particle doing any of these things, right? If you had a particle going like that, it would just, this part would get blocked, it would stick, and that part would keep going, right? If you did a particle with this, the particles would get through, and then this part would get blocked. Particles would get blocked there. They would go by fine here, but they would not spread out around the barrier like we see with waves. Let's take a look again at the idea of interference, which again is an idea from Physics 20. Okay, however, we're just building up our knowledge of waves a bit so that we can appreciate where we're going. Okay, so interference, I don't even like that. When waves interfere, they follow the superposition principle. Yes, light's a wave, but when waves interfere, they follow the superposition principle. So what is that? Well, you have two types. You have constructive and destructive interference. So the superposition principle is pretty simple. They add. Okay, they add algebraically. You can add a negative to a positive and they cancel each other out, right? So when crest meets crest, they add, giving you a big crest. So we can imagine a crest going this way, okay, could meet a crest going this way. And what would happen? They would add to give you a big crest. So one with twice the amplitude, or whatever blues plus reds is, okay? And then they would pass each other and continue on as if nothing had ever happened. So if we were to say that this was an amplitude of 1A, okay, then this thing would have an amplitude of 2A, right? If this thing has an amplitude of A as well, then you add red's amplitude to blue amplitude, and you get twice the amplitude, okay? When trough meets trough, they add, giving you a big trough, okay? Now, here's a common mistake. You say, oh, trough meets trough. That's destructive interference. No, right? They're helping each other. Trough meets trough. Those are the same thing. You get a big trough. They construct each other, okay? They don't destroy each other. Destroy each other means they cancel out, okay? -1 plus -1 doesn't cancel itself out. -1 plus -1 is -2, okay? So it is still a bright spot. We'll get there with light in a sec, but a big trough is not no wave. It's a big trough, okay? So this is still constructive interference where they are building each other up. So what would that look like? Trough moving this way meets a trough moving that way, okay? What happens when they meet? You guessed it, okay? A trough that's as big as those two things added together. So again, if this is the amplitude, if this is A, right, and this thing's amplitude is A, then what do you think this thing's amplitude is? Yep, 2A. Okay, now this works. You could also have, for example, these two troughs meet. If this was -1 and this was -3, then they would meet and have an amplitude of -4. Okay, so when do you actually get destructive interference? When they cancel each other out. Okay, so when a crest meets a trough. So when a crest and a trough meet, you get a dark spot. You get no light. Okay, so when a crest and a trough meet, so let's take a red crest and a blue trough. If the blue trough heads this way, the red crest heads that way, we could say this is A and this is -A. Okay, let's call these -2 and then call this -2A. Okay, now if they head towards each other, what do? Well, add that in your head to that. You get a flat line, right? Zero, no amplitude for that brief moment when they meet. Destructive interference. We went from a crest and a trough to nothing, no wave, okay? Again, we can kind of visualize this here. Okay, if we had this wave line up when it met this wave like this, okay? We have crest meeting crest, trough meeting trough. We would get a whole bunch of constructive interference, right? Constructive, they build each other up, okay? They make each other stronger, whether that's crest or trough, they make more of it. So they would be twice as high. They would have brighter. However, what if this wave met this wave? Okay, what if this wave, okay, what if it met this guy where it was at a trough here, crest here, trough, crest, trough, crest, trough. Notice how they're perfectly, whenever you have a crest in the red wave, you have a trough in the blue wave. Well, those would add up to give, you guessed it, no wave at all. Okay, no wave at all. Okay, so let's put these ideas together now. Let's put Huygens principle together with interference, okay? And again, pretend we're just talking about waves. You don't even need to be thinking about light just yet, okay? So when waves encounter two or more openings, okay, they begin acting like point sources because of Huygens principle, right? So all of these little wavelets are coming in and they just happen to all be propagating out like that. So when you draw a tangent, they just look like a straight line. However, if a whole bunch of them get blocked, well, now these ones are going to start just doing their thing there. And these ones are going to start doing their thing here. What did we say? When two waves meet up, they will interfere with each other. They will add together. Now, if a crest meets a crest, you will get constructive interference. If a trough meets a trough, you will get constructive interference. But if a crest meets a trough, or vice versa, then you will get destructive interference. I'm going to go back to here. We can make two point sources, make two waves, right? Those can definitely interfere. Crest meets crest, you get super crest. Trough meets trough, you get super trough. But where crest meets trough, you get these destructive interference lines, okay? Okay, so they have this tool here we can use to measure the water level. So notice when I put the sensor there on that destructive interference line, almost no movement at all, right? But if I put it in the middle on a constructive interference line, where crest is meeting crest and then trough is meeting trough, you get super crest, super trough, super crest, super trough, right? But if I put it again down here on the destructive, where crest is meeting trough, they cancel each other out and you don't get much of a wave at all. Okay, so this is it just as 2 point sources. Now we can imagine, because of Huygens principle, right, these wavelet fronts are coming in, hitting the barrier. Most are getting blocked, but these little new ones, now they act as new point sources, just like the drips in the water before, right? And so 2 point sources, that's 2 sets of waves, they're going to meet up and they're going to constructively here or destructively here interfere with each other. Okay, and you can see that happening again if we use our sensor. Notice these bands here of destructive interference. If I put the sensor there, not much of a wave happening. But if I go here, pretty big waves happening, right? Where they're meeting up. Okay, right on that band there of destructive, not much. So we knew this about waves. We knew very well that waves diffract, and we knew very well that they interfere. Okay. So what's the point of all this? Well, would you agree that particles would definitely not do this? Okay. This was one of the kind of big things that we needed to look at to decide for sure whether light was a wave or a particle. Yes, we're still talking about that, okay? It's important to understand the huge evidence for light being a wave. So I'm going to jump here to Young's double slit experiment, okay? So if light is a wave, it should diffract, right? Can we agree on that? If light is a wave, it should diffract by Huygens principle, okay? Now, if light diffracts, then when we pass it through 2 narrow slits, it should turn it into 2 point wave sources, okay? Now, if it's a wave, 2 wave point sources will produce waves that interfere with each other and produce a pattern on a screen like the ones on the previous page, okay? We should be getting bands of, so I just want you to watch what happens to the levels here as I go up here. So you'll notice, okay, here there's decently constructive interference, right? We're getting pretty big waves there. We're just watching the sensor here. Now, as I go there, though, I get destructive interference, right? As I go there, I get destructive interference. Much smaller waves. It's just because I can't quite find the exact right spot, right? Much smaller, and then bigger constructive interference. And then a band of destructive interference. Much smaller wave there, right? Barely any motion, okay? Constructive, okay? Destructive, because that's where these bands are happening. Constructive, destructive, right? These bands of constructive and destructive interference. Okay, so like we saw in the simulation, right? We should get these bands of constructive and destructive interference. What do you think that means for light? Well, constructive interference for light is brightness. It's going to increase the amplitude. Amplitude is the brightness of light, okay? So if we can increase the amplitude, if we can get constructive interference, we're going to get bright spots. But if we get destructive interference, what do you think? Well, what happens when you have no light wave? It's dark, right? If you cancel out the amplitude and you have no light, it's very dim or dark, okay? So Young decided to do this experiment, and don't get me wrong, people had thought of this for a long time. Can we make an interference pattern with light? And we didn't know, though, just how small the wavelength was of light, right? People were just putting 2 lamps next to each other and expecting to see it. The problem with that is that, first of all, lamps emit random bursts of different wavelengths of light. You need to kind of make sure it emits in the same phase, okay? The other thing is that the wavelength is so small that to get a good interference pattern, you kind of need the separation distance of the 2 point sources to be within a few wavelengths of the light, right? Once it goes way beyond that, then a diffraction pattern might technically be happening, but it's going to be so clustered that there'd be no way to actually tell, okay? So anyway, let's just compare the basics of this. So if light is a particle, what would we expect to see? So if light's a particle, it comes in, okay? So what Young essentially did, okay, is he sent light in, sent it through. He found a way to get very small openings. He actually split light up using a card, okay, and he had it go through 2 very narrow slits and said, okay, if it's a wave, we should see a diffraction pattern. So let's just see, what exactly was Thomas Young looking for? What were we trying to show here in Young's experiment? So if light was a particle, what would we have seen? We would have seen, well, this one would get blocked, right? That one would go through. Okay, that one would go through. Okay, these ones would get blocked. One would get through here. Maybe another one would get through here. Okay, that's what particles do, right? Imagine like spray painting over a stencil. That's the idea here, right? If it's a particle or bullets or something, right? You're shooting through, they'll get through the holes. They'll get blocked by the wall. They're not waves. They won't diffract. They're not point sources of outward radiation, right? So what would we see if it was a particle? We would see a bright spot here. Light would get through there, bright, and everything else would be dark, right? Up here, okay? But what should we see if it was a wave? Now things get interesting, right? If light's a wave, as it passes through to here, it becomes a point source of light. So these wavelets would get blocked, but this one, right? These ones that get through here will now start to radiate outward in concentric circles, just like they were before. It's just that now they're a little more on their own. They're kind of restarting, right? So now they go circularly outward and they start to spread out. Now, I'm just freehanding this, so it might not work out too perfectly, okay? But anyway, the same thing's going to happen down here. These wavelets are going to start spreading out. Okay, so again, just kind of freehanding it here, so it might not be too perfect, but remember, wherever a crest from one wave meets a crest from another wave, you get constructive interference, right? They add together. Same goes for troughs. Where trough meets trough, you get constructive interference, and they add together to be a super trough, okay? So let's say the lines I drew are the crests, so that means exactly halfway, half a wavelength are where the troughs are, okay? Let's go ahead and see wherever crest from the blue wave is meeting crest from the black wave. So that's just essentially where the lines cross, okay? So notice here we have, right, along that line, if I had drawn it a little more properly, we get really good, okay? But notice how crest is meeting crest and trough is meeting trough, right? The lines are meeting up and the middles are meeting up, okay? Same thing here, right down the middle. Oof, that one got off center a bit, but for the most part, okay, you can kind of see what I mean. Same thing going here. Constructive interference more or less on that line. Constructive interference more or less on that line. It kind of shifted that way a bit. Okay, now destructive interference is where a crest is meeting a trough. So where a crest is meeting a trough is where you have a line right in the middle of the other thing's wave, right? So this black crest is, see how it's in the middle of these two blue crests? So that black crest is in a trough, so a crest is meeting a trough. So that would be destructive interference, right? Along that line there. Same thing's happening here. Blue is in the middle of black, so a blue crest is where a black trough would be. Same thing out this way. Same thing out this way. So what would we expect to see if light were a wave and we passed it through two narrow slits like this? Well, we would expect to see a pattern, just like we saw in our waves, where it went very high, very fluctuating water level to barely the water fluctuating at all. We would expect to go from destructive interference. We would expect to see a dark spot, right? But then we would expect to see a bright spot, right? And then we would expect to see a dark spot. And then we would expect to see a bright spot. And if our picture went on long enough, we would expect to see that bright spot up there, right? And that dark spot up there if we had drawn a bigger picture and a bigger screen. So we would expect to see a pattern of light and dark spots, okay? Dark, where you have destructive interference, okay? Destructive interference, DI, and bright, where you have constructive interference, CI. That's what we would expect to see for light. And can you guess what Thomas Young saw? He 100% saw this, okay? So, light, without a doubt, sorry, Isaac Newton, light is a wave. Has to be. There is no way to explain this experiment without light being a wave, right? Because if light were a particle, what would it do?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
Okay, so don't believe me that this is what Young saw. You guys are never believing me, okay? That's okay, that's good. You should question it. So what I have here is actually just a hair. Now, what Young did, okay, is he didn't actually have two slits the first time he did this. He later did when he kind of refined it a bit. But he took something very thin, so imagine a lot thinner than this, but imagine something very thin like a ruler, okay? And what he did is he used that to split up the light so that some went over, some went under, and then because of Huygens' principle, on the other side of the ruler, right, they would end up as 2-point sources that could then go and interfere with each other. So what I have here is a hair from my own head. I just cut it off, okay? I'm going to shine this laser onto the hair, okay? And that hair is going to split, and it's going to act a lot like the card did in Young's double split the first time. Okay, so here I have a laser. I can even probably see when it hits the hair. And I want you to watch on the table behind it when I am hitting it correctly. Okay, do you see that? Notice how there's bands of light and dark, right? If I move back a bit, I can spread it out a bit. Do you see those bands, those light bands and those dark bands? Guess what that is? Constructive and destructive interference. Wow, that is super cool. Okay, I'm just doing that with my hair because the hair splits the light beam, right? Which essentially turns it into 2-point sources that then interfere with each other, and you get dark bands and light bands. Of course, a very bright one in the middle. How neat is that? Okay, so the key to understanding why we see these patterns, why they happen, is actually to think about the length of the path that the light has to travel, okay? So the key to this is what we call path difference or path length difference, okay? So the first point we're going to consider is the bright spot right in the middle, the central maximum we call it, or the central antinode, okay? And so remember, if a crest meets a crest or a trough meets a trough, we're going to get constructive interference. For light, that means a bright spot, okay? And so let's just consider we have now split our light into 2-point sources, right? We can explain that with Huygens' principle. The wavelets are now going to radiate outward, okay? So one path they could take as they radiate outward is to the central maximum, right? To the center, but point between. So let's think about the path that this point source here and this point source here have to take to the middle. Well, if you look at that, right, since the middle is by definition equidistant between the 2-point sources, right, then this is just now an isosceles triangle. So we can kind of already guess that they have to go the same distance, right? Let's think about that distance in terms of wavelength. So we have here, we can see it goes 1 wavelength, right? 2 wavelengths and 3 wavelengths. So from point source 1 to the point on the screen that we're looking at is 3 full wavelengths. Let's look down here. From point source 2 to that point, the waves are going to have to travel a distance that fits 1 full wavelength, 2 full wavelengths, 3 full wavelengths. So they're always going to be meeting at the same point in their wavelength, right? The distance represents the same number of wavelengths, whether you're at this point or this point, because of course it does. It's the same distance, right? So we can think of it as this many wavelengths fit in, right? That many wavelengths fit in, and then this many. And since they're having to travel the same distance, they're always going to meet. Crest is always going to meet crest. Trough is always going to meet trough, right? So we're always going to have constructive interference there. There's no difference in the number of wavelengths that fit into the path because it's the same path, right? So the path length there, since 3 full wavelengths and 3 full wavelengths, the path difference there is 0 wavelengths, right? There is no difference. The same number of wavelengths there and the same number of wavelengths there. But as we know, we get a pattern, right? We don't just get one bright spot. We would get, right? We've seen that you get light, dark, light, dark. So let's just move down now on our screen to a new point. So now you can probably tell that the path from this point source, since we're moving away from the center, this now has to go farther than the wave from this point source, okay? And so a different number of wavelengths is going to fit into this path as this path, right? So let's count them out. This guy has to go farther, and it's going to fit 1 wavelength, 2, 3. I don't quite agree with how they've drawn it and what they're saying here, but we'll say, okay, so 3.5 to that point there, and then they're saying 3 3/4. So 1/4, 2/4, 3/4. Okay, we'll give them that. But down here, it doesn't have to go as far. It has one full wavelength, two full wavelengths, three full wavelengths, and then up to another crest, right? So that's another quarter wavelength. So this one was 3.75 wavelengths. This one only had to travel 3.25 or 3.25 wavelengths. So the difference in their path lengths, if you do the math, 3.75 minus 3.25, that's 0.5 or 1/2 wavelength. So essentially what's happening is as this one's arriving, so this one has done 1, 2, 3, and this one is kind of arriving behind, right? So it's done a quarter, 1, 2, 3, right? And so notice what's meeting up here, right? Because it's shifted by kind of a half of a wavelength, right? Because it's 1/2 wavelength behind, well, half of a wavelength represents the difference from crest to trough, right? To go from a crest to a trough, that's 1/2 of a wavelength. Because if you do another half, that's a full wavelength and you're back to crest, right? And so if you're 1/2 wavelength behind, well, then crest is meeting trough and trough is meeting crest. And you're getting total destructive interference, or in the terms of light, that's a dark spot, right? So we go and we shift, and since this one doesn't have to travel, this one has to travel farther, this one doesn't have to travel as far, we've reached a point now here where that difference in their path length has added up to 1/2 of a wavelength. And so crest is meeting crest, trough is meeting trough, and we're getting destructive interference. We're getting a dark spot, a node, okay? But we can keep moving down and keep moving down, and this one will have to go even further as we continue, right? Because of the geometry here. So now if we keep going, we can reach another point where this point source, to get to that point down there that's even further, is going to have to go one full wavelength, two full wavelengths, three full wavelengths, four full wavelengths, and then 4.5, another half of a wavelength, right? Whereas this guy down here, yeah, it has to go a little bit farther than it did here, but it's not going to have to go as much farther as this guy did. Let's see. So this point source is going to radiate out one full wavelength, two full wavelengths, three full wavelengths. Hey, 3.5. Okay, so what we have now, okay, so what we said was this was 4.5 wavelengths, and this was 3.5 wavelengths. So that top one's had to go 1, 2, 3, 4.5. But the other ones only had to travel 1, 2, 3.5. So notice we're back to now, this thing has been shifted to being off by a full wavelength. And what that means for us is that once again, crest is meeting crest and trough is meeting trough. And so what are we going to get? We're going to get constructive interference all over again. We're going to get another bright spot. And that's exactly what we saw in our pattern, right? We saw bright, dark, bright, dark, bright, dark. And so this will continue. We could keep going, and this one would fall further behind again, until eventually it was far enough behind that it was 1/2 wavelength behind this guy one more time. And then what would you get? You would get destructive interference because it's a half wavelength, right? As soon as it's a half wavelength out of phase, you're getting crest meeting trough and destructive. But then we could keep going again, and it would be shifted 2 full wavelengths, and we would have crest meeting crest again and trough meeting trough again. So to kind of show you in maybe a more physically tangible way, right? We could have 2 waves, and they have to travel some path, right? So if they have to travel the same path, we can imagine, okay, they have to go the same distance, and since they have the same wavelength, crest always meets crest, right? This crest meets this crest, and they would add together, and the trough would meet the trough, and those would add together, and you'd get super crests and super troughs, right? But imagine now that this one has to go a little bit further, okay? And so they get more and more out of phase as they go. One kind of pulls ahead of the other because it doesn't have to go as far. And so if I shift it and shift it and shift it until, look at this, they're now 1/2 wavelength behind each other. What's happening? Crest is meeting trough, right? And trough is meeting crest. And so these would add together algebraically and they would cancel out. We would get no wave at all at that point. We would get a dark spot if the wave we're talking about is light. Okay. But if they continue, if they're even further out of step, right? If they're even further and they keep going, look where we get back to. Now it's one full wavelength shifted, right? One full wavelength fits now in the difference. And what do we see? We see crest has now lined back up with crest. Trough has lined back up with trough. We're getting constructive interference. Another bright spot. If we go even further, right, the difference becomes even greater and we keep going. Hey, we have to pass 1/2 wavelength again. And what happens there? Crest, trough, trough, crest, destructive interference. Even further, the difference becomes more pronounced, and we get back to now they're 2 full wavelengths. This one's now 2 full wavelengths longer that it's had to travel, right? And so what ends up happening, crest is now back up with crest, trough is back up with trough. It doesn't matter which crest meets which crest, it's just that a crest meets a crest, right? That's where you get constructive, okay? We can continue, kind of keep going. Another dark spot, another light spot, and in theory, this would go on and on and on. If you had 2 bright enough point sources, it kind of keeps happening. So I'm going to show you this animation here. It's already kind of underway, but what they're going to do is they're imagine 2 point sources, and they're going to analyze the different paths taken to certain points. So if we put a screen on this, then we're getting a diffraction pattern actually being produced. We're just going to look at the bands of constructive and the bands of destructive interference. So in a second here, it'll restart, but they ask you to take a look at this point here, and I'll just point out, okay, we have dark being crests, light being troughs. So they've actually drawn in the crests and the troughs, right? So from crest to crest is 1 full wavelength. They're going to take this point here, A, and they're going to analyze what are the waves arriving at A, where are they in their cycle if they arrive there from source 1, and where are they in their cycle if they arrive there from source 2. So let's just take a look once it restarts here. Okay, they're going to count out the wavelengths crest to crest. And so here's point A, and here they go. They're going to count it out. Count out the number of wavelengths from here to A. Okay, so it travels 1, 2, 3, 4, 5 full wavelengths, right? 5 full wavelengths fit to point A. Let's now look at what waves from source 2 will be doing at the time they hit A. So 1, 2, 3, 4, 5, 6. They're off by 1 full wavelength. As we saw, though, that still means crest meets crest. And you can see that by drawing out the wave crests here, right? Crest meets crest. And so we have constructive interference at that point. If we were to draw our screen right here, we would get a bright spot here. By the way, we could draw our screen here as well, or down here even, anywhere along that line that they've shown, right? Along the line you can kind of see here where crests are meeting crests and troughs are meeting troughs. That would be a bright spot. And again, we could do this at a different point. They've actually done it at the same point on the same line. It's just that now 3 full wavelengths and 4 full wavelengths. Still, though, you're 1 full wavelength behind, so crest is going to meet crest and trough is going to meet trough, and you're going to get a bright spot, constructive interference at point B here. What if we move off that line? What if we try a different one? Well, now look over here. We can count them. 1, 2, 3, 4 wavelengths from source 1 to point C. And then what about from source 2 to point C? We have 1, 2, 3, 4, 5, 6. So 4 full wavelengths, 6 full wavelengths. They've now shifted to be 2 wavelengths out of phase. Doesn't matter, 2 full wavelengths. Crest is still meeting crest. Trough is still meeting trough, right? That would be constructive interference. So again, if we drew our screen, we would have a bright spot here. If we drew our screen lower, if we had our screen closer to the sources, we would still get a bright spot there, right? This is the line where there's a path difference of 2 full wavelengths all the way out to there. Let's look now at destructive. So to get destructive, we saw that one source has to be sending out waves that are now a half wavelength behind. So crest needs to be meeting trough. So the dark lines need to be meeting the light lines, right? So you can kind of see along this line that that's all happening. Let's count wavelengths to see how that works that way. So from point D to source 1, we have crest 1, 2, 3, 4, 5. So 5 full wavelengths from source 1 to point D. What about source 2 though? 1, 2, 3, 4.5 wavelengths. So that means if you're a half wavelength behind, then when the other one's at a crest, you're at a trough, right? And so sure enough, crest meeting trough, destructive interference. What if we were to go here? Well, then this one would be 4.5, and this one would be 4, right? Still half a wavelength behind, and so you would still get destructive interference. If we had a screen here, that would be a dark spot. Okay, we can do it over here as well. 1, 2, 3.5. Here, though, look, 1, 2, 3, 4, 5. So it's not 1/2 wavelength behind, but it's 1.5 wavelengths behind. And so, again, we get destructive interference because that still means crest is meeting trough, right? Just like I showed with the paper, 1.5 wavelengths behind still means crest meets trough. Again, you can see it happening over here. That would be at 2.5. Okay, and here's kind of a summary of the whole thing. So you have essentially what these numbers, you can interpret them as, is the path difference, right? So to the central one, so the central one, we didn't actually look at that here, but if you take a look, right? 1, 2, 3, 4, 5, 6, 7 to this point, or 1, 2, 3, 4, 5, 6, 7 to this point from source 2. So those waves are always going to meet up and constructively interfere, right? Then as we go to the left or to the right, doesn't matter, the same thing's happening on either side, right? But if we go over here, now we always have trough meeting crest. Why? Because pick any point along this line. Let's do J, because they've labeled it. You have 1, 2.5 from source 1, but you have 1, 2, 3 from source 2. So that's a difference of 1/2, right? If we go to H, we have 1, 2.5 from source 1, and from source 2 we have 1, 2, 3, 4 full wavelengths. So 4 compared to 2.5, hey, that's a difference of 1.5, right? 1.5. So if they work out to be any multiple of a half wavelength off, you're going to get destructive interference, right? So if we had put a screen, right, we would get light, dark, light, dark. We saw that earlier with the laser and the piece of hair, right? Why light, dark, light, dark? Well, to go from having no difference, right, to getting to be one wavelength behind, you're always going to have to pass being 1/2 wavelength behind, right? And then you can get to 1 wavelength. And then if you want to get, okay, well, what's the next bright spot where I'm 2 wavelengths behind? You can't get to 1 from 2 without first being 1.5 wavelengths behind. So you will always have this pattern of light, dark, light, dark, light, and then on the other side, the same thing. So let's take a second now and think about this, right? What is the path difference as a function of wavelength in each case? Well, we already saw the central maximum, right? Of course, they're equidistant from the central maximum. The 2-point sources are equidistant. So the path difference there will always be 0. The same number of wavelengths is, of course, going to fit into the same distance. So 0 wavelengths, right? 0 lambda. Okay, now at the first order dark spot. So again, picture those 2 cards I had where one pulled ahead of the other. What's the first time that crest always meets trough and trough always meets crest? Well, it's when they're 1/2 shifted from each other, right? So when we have the path difference, the difference between them being 1/2 of lambda. After the central maximum, that middle bright spot, the next time you're going to see brightness is when you've gone past 1/2 all the way to now they're a full wavelength out of phase, right? So when they're 1 full wavelength away from each other. So if we draw it like this, right? So again, starting at the central maximum, they don't have any path difference, and so it looks like that, right? Of course, constructive interference there, crest is meeting crest. Then as one gets as one doesn't have to go as far, they're going to end up shifted, and as one pulls ahead, as the red one pulls ahead here, right? You can see that, okay, we have to pass that first dark spot. When do we do it? Well, when we've moved the crest over by 1/2 of a wavelength, right? See how by moving where a crest was to where a trough was, that's shifting it by 1/2 of a wavelength, because crest to trough is 1/2 of a wavelength. As we keep going, as this red one gets more of a head start, right? Keeps going, keeps pulling ahead. Aha, we hit the point where crest is meeting crest again and trough is meeting trough again. So we have, once again, constructive interference. That's the first time that happens after our initial central maximum, right? So first order dark spot there, first node, first order bright spot. We call the central one the 0th order. Okay. Now, what's the next time we're going to get a dark spot? Because we want the second order dark spot, the second order node. Well, we keep going. Let's keep going, keep going, keep going, keep going. Aha, there it is. How far have I shifted this thing? Well, it started out there, right? Now it's gone, right? Now, 1 full wavelength, and then another 1/2 one is how far I've shifted it, right? So the second order dark spot is on the way from the first to the second bright spot. And so what's smack dab in the middle? 1.5 wavelengths, right? Once you've shifted it 1.5 wavelengths, you get another dark spot. Keep going till we get to the next bright spot. Keep going, so keep shifting until we get constructive interference again. And where's that? Lo and behold, 1 full wavelength, 2 full wavelengths, right? Now crest is meeting crest again because we've done an integer number of wavelengths again. So that will happen when we've gone past 1.5 all the way to a path difference of 2 full wavelengths. Are you starting to see a pattern here, right? The second time we'll see bright spots is once we're at 2 full wavelengths, right? The first time was at 1 full wavelength, okay? So reminder here, antinode means bright spot, constructive interference. Node means dark, destructive interference. So the 7th order antinode, in other words, the 7th time that we will see constructive interference, that we'll see a bright spot. Well, again, like we said, the first time is when they're 1 full wavelength behind, not counting the middle. That's kind of considered the 0th time, right? The first time will be when they're 1 full wavelength behind, then second time will be once they're 2, and then the third will be once they're 3 full wavelengths. So you can probably guess by the time we hit the 7th order bright spot, how many wavelengths behind is 1 wave? 7. 7 full wavelengths, right? 7 lambda. Now the 6th order dark spot, okay, be careful here. So the 6th time we see darkness, remember, the first time was when they were 1/2. The second time was when they were 1.5. The third time would be when they were 2.5, 3.5, 4.5. You count off on your fingers, you'll see that the 6th time we get a dark spot is once we hit 5.5 wavelengths, okay? And we've kind of arrived at an idea here. Let's just say n is the number of the bright spot or dark spot that we see on either side of the central maximum, okay? So if we say n is 0 for the central maximum, then the first dark spot will be the dark spot where we say n is 1, and the first bright spot will be where we say n is 1, and then the second will be n is 2, and the third will be n is 3, and so on, okay? So yeah, the first dark spot is at 1/2 of a wavelength, but what we could think of it as is go to the first bright spot, go to where you have 1 full wavelength difference, and then go back half a wavelength, right? In other words, 1 minus 1/2 lambda, right? Go to the bright spot and then go back half a wavelength, and that's where your dark spot will be. What about the second order dark spot? Well, go to the second bright spot and then backtrack 1/2 of a wavelength, okay? The 6th one, go to the 6th bright spot and then go back 1/2 of a wavelength. So 6 minus 1/2 lambda, okay? And what you'll notice here is that if n is the number of bright spots as you're counting out, well, every time we're going to get a bright spot is when we are 1 full integer multiple of a wavelength away from that central maximum. So for constructive interference, okay, bright spots or antinodes, we will see that whenever we're 1 full integer wavelength away in terms of path difference. So the path difference must be n times lambda, where n is 0, 1, 2, 3, 4. And that will tell us the path difference. Okay, so the path difference, PD, is n lambda. Now, what about for destructive? Those are dark or nodes, okay, where we have crest meeting trough. Well, when did that happen? It happened when we were 1/2 wavelength away, when they were 1/2 wavelength out of phase, right? So in other words, go to the first bright spot, so at the first dark spot, n equals 1, right? And then subtract 1/2. So n minus 1/2 lambda. At the second one, 2 minus 1/2. At the 6th one, 6 minus 1/2. So to get destructive interference, the path difference must be n being the number of the dark spot that you're looking at, and then subtract 1/2 times lambda. So the first time you'll get that is just before the first bright spot. So n being the number of the spot you're looking at. So the first dark spot, n is 1. For the first bright spot, n is 1. Okay, this is very important to know. Okay, and I'm going to do the math examples and the formula stuff in another video, but I do want you to quickly look at your formula sheet right now. Okay, there are 2 formulas related to this stuff, and they are under the waves section on your formula sheet, and they're the bottom 2 on the right side. So right column, bottom 2 formulas. You have lambda equals d sine theta over n, and lambda equals xd over nl. Again, those are derived pretty well in your textbook. It really just boils down, again, to geometry and making triangles. Okay, I'm not going to go too much in the gory detail of deriving them. However, you will notice they only have n there, right? N lambda if you multiply n by both sides in both equations, okay? They do not have destructive interference in there. So these are not one-size-fits-all equations. These equations, as they're written on your formula sheet, are only for constructive interference. How do you fix that? If you know you're analyzing a dark spot, if you're looking at a node or destructive interference, you need to put the 1/2 in on your own. You need to know to do that, okay? So I'm going to make that note here. Okay, so again, the equations on the formula sheet are only set up for constructive. If you're dealing with a dark spot, you are responsible for putting in that minus 1/2 to say, well, we're not getting constructive interference, we're getting destructive here. So it's actually an integer multiple of the half wavelength off, not just an integer multiple of the wavelength off. Okay, so just to kind of apply this a bit, let's think about it. If the path difference to the second order node, okay, node, what does that mean? Destructive, dark, okay, is 3.5 nanometers. What is the wavelength of light used? So it's saying as we go from the central maximum to the first order maximum or the first order antinode to the second one, along the way, we have to pass the second order node. So if by the time the light gets there, the difference between them is 3.5 nanometers, well then what's a full wavelength? So the path difference for destructive interference equals n minus 1/2 lambda, okay? What's n gonna be here? 2, right? Because we're at the second order node. So it's the second time that they meet up 1/2 wavelength out of phase. Okay, we're looking for lambda, so lambda equals the path difference over n minus 1/2. And so if 3.5 nanometers represents a 2 minus 1/2 or in other words, a 1.5 or a 3/2, okay? If that represents that much of a shift, well, then what's a full wavelength? Lambda equals, I got 2.3 times 10 to the minus 9 meters. Or if you'd rather, 2.3 nanometers. So just thinking about if it's shifted by that many multiples of half wavelengths, by the time it gets to there, then what is a full wavelength? Okay, so just a kind of a cool instance of this happening, something called Poisson's spot. Okay, so it's named after a mathematician. And this guy, Poisson, he was a big light as a particle guy. Okay, he's a very big Newton fan. He was definitely on Team Newton for this whole debate. And so when some evidence like Young's double slit experiment started coming out that said light really behaves like a wave, right? And some mathematicians like Fresnel had come up with some equations that worked pretty well to describe light's behavior. Poisson kind of took it upon himself as a mathematician. He said, no, look at these equations. Look what they're saying. They're saying that if you have some kind of spherical object, right, then because the distance on a circle to the center is always the same, right? It's always the radius of the circle. No matter where you are on the edge, the distance into the middle is just the radius of the circle. So these are all equidistant from the center, right? Well, then, according to you guys, we should be seeing a bright spot in the middle of a shadow that has a shape of a circle, right? And he just thought that was ridiculous. And a lot of people kind of did this. That does seem kind of ridiculous. If you have a shadow of a circle, the center of it should be the darkest spot. There shouldn't be a bright spot there, right? So Poisson kind of did this kind of smugly and said, this is dumb, right? And we hadn't ever seen that. But we also got to remember, we didn't realize how small light wavelengths were, right? So experiments to look for Poisson's spot hadn't necessarily been able to take that into account. But eventually, Dominique Arano, he did perform an experiment that allowed this to happen. And actually, during a solar eclipse where the moon is the circular object blocking the sun, you can observe this spot. But lo and behold, he did actually discover, you can kind of see it there. See that little bright spot? That's because the path difference here is 0. All the paths from the outside, so if we take Huygens' principle, where all these light waves encounter this circular object and start spreading out concentrically, guess what? They're all going to have to take the same path to the center, and you're going to get a little bright spot at the middle. And so when this was discovered, it has a few names. Some people named it after Fresnel. Some people call it by Arano. But actually, the most common name for it is Poisson's spot. They kind of flexed on him by naming it Poisson's spot because he had been the one that had smugly kind of said that this should exist, and clearly it doesn't, right? And so it just goes to show sometimes we're remembered for our greatest achievements, other times we're remembered for our greatest failures. Okay, I'm going to pop a little bit ahead in the notes just because I'm going to do the theory first. I just want to talk about something called diffraction gratings, and then we'll come back to that other stuff really quick. Okay, so diffraction gratings, there's no really new physics here to think about. It's just a different application of these ideas of destructive and constructive interference by splitting up one light source into little point sources. Okay, so essentially what is a diffraction grating? It's just making tons of slits instead of just two. As long as you keep the distance between them the same, then you have a whole bunch of point sources that have to take a whole bunch of different paths to points on the screen, right? And because they're all the same distance apart, they always kind of arrive in the same multiples or 1/2 multiples or 1.5 multiples of their wavelength, right? And so how can we get a whole bunch of slits? You can't get that many onto like a piece of cardboard or something, right? So scientists kind of had the idea, take a piece of glass and just scratch a whole bunch of parallel lines on it and make sure they're evenly spaced. Why scratch into glass? Have you ever driven in a vehicle where like a pebble had hit the windshield and you had a crack, right? What do you notice about the light getting through? Does it get through the crack very well? No, right? It's kind of a dark spot where the crack is. That's because cracked glass does not let light through very well at all. So if you put a whole bunch of scratches into it, what you're now essentially going to have is a bunch of slits that allow light through here, okay? So light gets through, and then light doesn't get through the scratch. So what you've done is made a whole bunch of little slits, all evenly spaced, and that makes a whole bunch of little point sources, okay? So the physics happening here is nothing different. It's just that more of it is happening. So more interference is happening. It still all comes down to path length. It still comes down to constructive and destructive interference. You're just doing more of it, and what that allows is a more pronounced image. The only difference, and I'll go over this more in the math example video on the next one, okay? The only difference is that now we kind of have to figure out, based on the number of scratches in a length of diffraction grating, how far apart are the slits, okay? So that will come when we do the formula stuff. I just wanted to introduce the idea of a diffraction grating so I can show you them in this video. Okay, Now back to the last thing for this idea so that I can now show you with a diffraction grating. Okay, something we've kind of been leaving out is how does this depend on the wavelength of the light? We know that whether we get bright or dark depends on how many multiples or half multiples of the wavelength we are off from each other, but we haven't talked about how different wavelengths are affected. So the SparkNotes version is that the amount of spreading, okay, so the amount that you're going to see spreading between bright spot and bright spot or dark spot and dark spot is directly proportional to the wavelength. So we can get more diffraction, more spreading, okay, from the wavelength, directly proportional. In other words, okay, so sine theta, in other words, sine theta, where theta is the angle of diffraction, how much it spreads out from the center, is directly proportional to lambda. So bigger wavelength, more spreading. Okay, think back to refraction. Careful, this is the opposite. So remember, when we were doing refraction, okay, when we were doing refraction, blue bent the most, or I guess violet bent the most, right? Red bent the least. Red had a bigger wavelength, and refraction is inversely proportional to wavelength. In diffraction, they're directly, so it's actually the opposite. Red diffracts more than blue, and as we saw before, blue refracts more than red. So I'll show you that in a sec with a diffraction grating, okay? But essentially, it's the opposite of what we did with refraction. The other big difference there too is that refraction, you just had one beam that got spread one way because it was encountering one interface. In diffraction, remember, light kind of spreads out circularly from those point sources, and so where they meet up is going to happen on both sides of the center, right? So you're going to get kind of two spectrums produced. So you're going to get two spectrums produced, well, two spectrums produced over and over and over as you go out and out and out and out. Okay, and you'll see what I mean in a sec. You can also, by decreasing the gap between the openings, okay, so in other words, by moving the slits closer together, you will spread the light out more. Okay, and again, the geometry is the explanation for that. You can check the textbook for the derivation if you want, okay, but by moving the gaps closer together, by bringing the slits closer together, you will make the pattern more spread out. So another way of saying that is that sine theta is inversely proportional to D, which is the spacing between slits. Again, I will go into the formulas more in the next video, but if you want, you can try them. You can see them here pretty much, right? Try those out. See how they compare. See how lambda compares to D, and see how lambda compares to the wavelength if you make one bigger. Okay, now I'll just kind of show you these with an actual diffraction grating so you can see the relationship between these variables. Okay, so I'm going to look at the second one first. Actually, I'm going to look at the difference in the spreading of the pattern based on the spacing between each slit. Okay, so I have here 3 diffraction gratings. Again, nothing fancy, just glass with scratches in it. Okay, just very carefully placed scratches. So you'll see we have one here on the left that is, 100 lines per millimeter. Okay, so in every millimeter, there's 100 scratches, right? Then we have one that has 300 lines in every millimeter. So bigger number there actually means they're closer together, right? If you have 100 packed into a millimeter and then you have 300 packed into the same millimeter, the 300 ones are going to be even closer together. So we're actually making the separation distance smaller when we put more lines in a millimeter. So 600, obviously, even more, okay? So I'm going to take a laser here. I have a green laser, okay? I have a green laser, okay? The reason I'm using a laser is lasers are what we call monochromatic, one chromatic color. So they produce light that's kind of one good wavelength so that we can get that clean interference pattern instead of getting different wavelengths diffracting a different amount and kind of blurring together, okay? So taking this green laser here, I'm going to first shine it through the 100 lines per millimeter. So that's the one where the D, the separation distance between slits, is the biggest out of these 3 options, okay? So I'm going to hit that, and look at that, diffraction pattern, right? Those are nodes and antinodes, bright spot, dark spot, bright spot, dark spot. Pretty cool, okay? Let's go to the 300 lines per millimeter. So now more lines packed into 1 millimeter. They are closer together, smaller separation distance between the slits. Look at that, spreads out. So again, there's 100, there's 300. Let's now go to 600, right? Look at that, even more spread out. You can actually only, on the screen, we can only fit the first order antinodes, the first order bright spots, okay? Can you even see those actually? Okay, pretty neat. Notice the central one is always the brightest, right? And they dim out as they go, right? It kind of gets dissipated as you go. Okay, the second relationship we talked about was the relationship between wavelength and the spread of the pattern. Okay, so if I put red and green both on there, which one has a longer wavelength? Well, Roy G. Biv, right? Red has the biggest wavelength of the visible light. green somewhere in the middle. So red has a much larger wavelength, and as a result, that should mean it spreads out more, right? As we just kind of talked about. So if I draw from the central red to the first order bright red, okay, that's the distance I'm getting. And then if I go from the central green to the first order bright green, you'll see that the green spread is much smaller than the red spread. Or maybe I need to turn them off for you to see, right? That's the spreading we were getting. So shorter wavelength, less spreading, unlike refraction where it was the opposite. Now, great for when you're dealing with monochromatic light, right? One color. But what if you have white light, which is a combination of all the colors? Well, here I have a ray box producing a white ray of light, again, composed of all colors, the same ray box we used in refraction to split them. How would diffraction split them? Based on the relationship between spread due to refraction and wavelength, because it's the opposite relation, right? So if I place the diffraction grating in front of this white light, you'll notice I can also produce a spectrum that way and put the screen here on this whiteboard, okay? I still get that central bright maximum. Why is it white in the middle still? Well, think about it. None of the waves have to take a different path to get there. So they all kind of get recombined back again into white. However, as they get spread out, then the wavelength dependency does become relevant because different ones get spread out more. Here, there's really no spreading happening, right? They're just kind of coming back to where they were. Out on the fringes, though, on the first order bright spots, you can see there's a spectrum forming. Notice on this spectrum, unlike before, the least bent is now purple. Purple's on the inside, right? Violet's on the inside. As it goes outwards, you see the spectrum produced out to red, right? Violet to red on the bottom, violet to red on the top. Now you might be saying, how come there's only one? There are more. It's just fainter and fainter and fainter as you go. So look, I can go, for the cost of image clarity, I can do fewer slits so that less of this interference is happening. But what I will get is more nodes and antinodes, right? So if I do the 100 line, that means I bring the slits farther apart, right? And as we said, inverse relationship between slit distance, okay? Now I can actually fit more of those interference patterns onto this page, and they're brighter the middle. So now you get a bunch of little spectrums, right? Little repeating spectrums, but always you can see that it's violet to red up here, right? Violet to red. Violet is the least bent, red is the most. Down here, violet's the least bent, red is the most bent. So key point here, you are going to get more than one spectrum for diffraction because it's spreading out on both sides, and also that it's going to be the opposite as refraction, where you had red bent the least, blue bent the most. Totally opposite now, okay? And more than one spectrum produced. One final way we can actually kind of look at this splitting due to diffraction of the component colors of white light is by splitting the light on its way to your eye, or your camera, which is your eye for this course now, okay? So I'll hold it up to the camera, right? And you can look, notice again with the 100 lines, which has the biggest distance between slits, right? They're the most spread out because there's only 100 in a millimeter. You get the least spreading out of the interference pattern. So what's happening? Why are you seeing so many of me? Well, light is leaving me, entering the diffraction grating, and then entering those slits, and then constructively and destructively interfering. So we get a bright spot here where another image of me is being produced, right? As we go out and as we go out. You can kind of see it's dark in between the bright spots. So, and then as we go to this one, closer line spacing, because there's more lines, see these images are now a little more spread out. And as you go to this one, they actually get so spread out that they get kind of hard to see, okay? But I want you to notice something too about the different versions of me that there are. Okay, so I'll hold up my finger so you can see. So you can kind of tell the one in the middle that looks somewhat correctly colored, that's the central maximum of my finger, right? That's a central maximum forming on your eye. But if you go to any one to the left or to the right, notice that it kind of goes violet to red, right? So the violet component of white light that's bouncing off my finger gets bent the least. And so that's why it's closer to the central maximum. Notice how if you pick an image of my finger, it's red on the outside and violet on the inside, the middle one being kind of normal colored, right? Because all of those wavelengths are combining back together. So violet to red from inside to outside. Least bent violet, most bent red. Okay, so we haven't even actually touched on the formulas yet. Again, that will be in the next video. But this wraps up the theory part. So if you're looking for questions that kind of go with this stuff, check the agenda or the Google Classroom for topic 3 stuff.